In this video, we are going to be doing revision by solving some past topical questions on stoichiometry, electricity and chemistry, that is electrolysis, chemical energetics, and chemical reactions. Before we continue with our topic today, I want to appreciate those of you who have taken your time to subscribe to our channel. For those of you who haven't subscribed to our channel, please support us by liking this video, share to other learners, and take your time to subscribe to my channel. Thank you very much for taking your time to subscribe to my channel. Let's get started. We are going to start with question number one. Question number one. Sodium hydrogen carbonate is found in baking powder. When sodium hydrogen carbonate is heated, it forms three products. This is the equation. NaHCO3 will give us Na2CO3 plus water plus CO2. The question is, A, name the type of reaction which takes place when sodium hydrogen carbonate reacts in this way. Fellow learners, when you see a reaction in this, a reaction decomposed in this way like this, a reaction that is being broken down into other products like the sodium carbonate, like water, and there is carbon dioxide from sodium hydrogen carbonate. We call this type of reaction thermal decomposition. It is thermal decomposition because it is heated. After heating, three other products result. We call this thermal decomposition. Thermal decomposition. Thermal decomposition. That is the name that is given to this type of reaction, thermal decomposition. B, calculate the volume of carbon dioxide formed at room temperature and pressure. Room temperature and pressure when 12.6 grams of sodium hydrogen carbonate is heated under the following steps. Determine the mass of 1 mole of sodium hydrogen carbonate. The molar mass of this can be determined as follows. We have sodium hydrogen carbonate, that is sodium hydrogen. Sodium hydrogen carbonate, we can get the molar mass as from the periodic table, from our periodic table provided on the question paper. you will have sodium is 23. The mass of sodium sodium is 23. Hydrogen is 1, that is plus 1. Carbon is 12, that is plus 12. Then oxygen is 16, but there are 3 atoms of oxygen here. So it will be 16 times 3. If we add up all these, we are going to have 84 grams, 84 grams per mole. It's supposed to be 84 grams per mole. That is 84. Here we have 84. Now, calculate the number of moles of sodium hydrogen carbonate used. Okay, the number of moles of sodium hydrogen carbonate that are being used from our equation, from our formula. If you go back here from what we know, number of moles, the number of mole is the mass. Here, you can see it here. The mass, moles will be the mass divided by the formula mass or the atomic mass. The formula mass or the molar mass we got here was 84. So now, what we are going to have here will be the number of moles the moles will be the mass all over the mR. Now, which will be equals to what? What was the mass? The mass that was given was what? Sodium hydrogen carbonate did what? 12.4. When 12.4 gram. 12.6 gram. So it will be 12.6. 12.6 gram. Yeah, 12.6 gram divided by this other one is 84 gram per mole. 84 gram per mole. And if we cancel out all these, the gram will cancel the gram. Okay, 12.6 divided by 84. What we are going to have will be 12.6 divided by 84. What we are going to have will be 0.15, 0.1515, which will be equals to 0.15 moles. 0.15 moles. Now, determine the number of moles of carbon dioxide formed. The number of moles of carbon dioxide formed. Moles of carbon dioxide. The moles of carbon dioxide, we can only determine it, we will determine it here. Okay, let me say moles of carbon dioxide. Let me show you how to do it from our equation. From our equation here, remember you make use of your equation, please. This is stoichiometry. So number of moles of carbon dioxide that are formed. Now we want to make use of our equation. So we must first of all write our equation out. Our equation here is our equation is that is 2 hydrogen carbonate. When it decomposes, it gives us sodium carbonate plus water plus carbon dioxide. Now, we have been told calculate the number of moles of carbon dioxide produced. In order to calculate the number of moles of carbon dioxide produced, what we need to do here is we will now say if 2 moles of sodium hydrogen carbonate can produce 1 mole of carbon dioxide, then the number of moles of carbon dioxide that we calculated here will produce how many moles of carbon dioxide? Okay, we can now say if from this equation, if 2 moles if 2 moles sodium hydrogen carbonate can give 1 mole. It's only 1 mole of carbon dioxide here. 1 mole carbon dioxide. Therefore, we had 0.15 moles of sodium hydrogen carbonate here. Therefore, 0.15 moles of sodium hydrogen carbonate will give X. It will give X. And if we calculate our value of X, we give X moles of carbon dioxide. Now X will be what? X will be 2 will be 0.15 times 0.15 times 1 divided by what? Divided by 2. 0.15 divided by 2. 0.15 divided by 2. We will have 0.075. We will have 0.075 0.075 moles carbon dioxide. Those are the moles of carbon dioxide. Moles of carbon dioxide. But we were told determine the number of moles of carbon dioxide formed. That is it. So the number of moles of carbon dioxide will be what? I said the number of moles of carbon dioxide will be 0.075. From our equation, we can say 2 moles. Calculate the number of moles of carbon dioxide. 2 moles sodium hydrogen carbonate will give how many moles? Will give 1 mole carbon dioxide. Therefore, 0.15 sodium hydrogen carbonate will give X carbon dioxide, which will be equal to what? Our X will be equal to what? 0.075 moles of carbon dioxide. That is the number of moles of carbon dioxide that are formed. That is it that we have just calculated here. Now, we will have to use this to calculate the volume of carbon dioxide formed at room temperature and pressure. The molar volume of a gas is at room temperature and pressure. That is the molar volume of a gas. The molar volume of a gas at room temperature and pressure is 24 dm cube or 24,000 cm cube. Now, okay, volume of carbon dioxide formed. 1 mole of a gas at room temperature and pressure. Now, volume of carbon dioxide formed at room temperature and pressure. Okay, note 1 mole of a gas at room temperature and pressure. 1 mole. 1 mole of a gas at room temperature and pressure occupies 24 dm cube. Occupies 24 dm cube. You can store 24 dm cube or you can store 24,000 cm cube. Therefore, now the volume of oxygen was, I mean the number of moles of oxygen is what? 0.025, 0.075. Therefore, 0.075 moles of carbon dioxide will occupy, will be what? Will be, that will be 0.075 times 24 times 24 20 times 24 dm cube, and that will be what? It will be 1.8. It will be 1.8 dm cube. Yeah, 1.8 dm cube is already there. So that will be 1.8. So the volume of carbon dioxide will be 1.8. So you have got the moles of carbon dioxide. Use the moles of carbon dioxide to calculate the volume of carbon dioxide formed at room temperature under pressure. So it should be noted that 1 mole of a gas at room temperature and pressure occupies 24 dm cube. Occupies 24 dm cube. Therefore, 0.075 moles of carbon dioxide, 0.075 moles of carbon dioxide will be 0.075 times 24 dm cube, which will give us 1.8. Will give us 1.8 dm cube. Okay, if you do that, we go back to the C part of the question. The C part of the question says, lime water is aqueous. Lime water is aqueous calcium hydroxide. Carbon dioxide turns lime water murky because a white precipitate forms. Because a white precipitate forms. Write the formula of calcium hydroxide. Write the formula of calcium hydroxide. Calcium hydroxide is, this is the formula of calcium hydroxide. You will write this is calcium. That is the formula of calcium hydroxide. Now, the white precipitate that forms when lime water turns murky. The white precipitate that forms when the lime water turns murky. What will be the white precipitate? The white precipitate that forms when lime water turns murky. Okay, let's go back to our question. For the purpose of revision, when when carbon dioxide turns lime water murky. Okay, okay, lime water is calcium hydroxide. Let's see the reaction. The reaction will be carbon dioxide. This is carbon dioxide. When it reacts with lime water is calcium hydroxide. What will be the product? When it reacts, there is a calcium carbonate that is being formed, and water. This is the calcium carbonate, which is solid, and this is this. Therefore, this is what causes the precipitate. This is the precipitate that is being formed. This is the precipitate that is being deposited, which is the calcium carbonate. We go back to our question paper. The white precipitate that is being formed, the white precipitate that formed when lime water turns milky would be calcium carbonate. Calcium carbonate. Now let's go to question number 2. Our question number 2 has to do with electricity and chemistry. That is electrolysis. It has to do with electrolysis. Now, a student carries out an electrolysis experiment using the apparatus shown below. Look at the apparatus very well. You see the connecting wires from the electrodes, the carbon electrodes, the 2 carbon electrodes that are being dipped into the electrolyte, which is the dilute aqueous sodium chloride. The student uses dilute aqueous sodium chloride. The question now says, state the name given to any solution which undergoes electrolysis. For a solution to undergo electrolysis, that is the breaking down of the compound into the respective ions by passing it through a current of electricity. So that type of solution which will undergo this process is called what? It's an electrolyte. This is an electrolyte. This solution here is an electrolyte. So we give the name the electrolyte. Electrolyte. That is the name that has been given, electrolyte. Hydroxide ions are discharged at the anode. Hydroxide ions are discharged at the anode. Complete the ionic half equation for this reaction. Hydroxide ions are discharged at the anode. Complete this. Okay, if this is the anode is the positive electrode. If the hydroxide ion are discharged at the anode, now what this must do will be what? We want to balance it. Okay, what is this? What is released? Oxygen is released. Oxygen is released. There's OH here. There is OH here. OH minus. and there's oxygen here. Hydrogen is still there left. So what will produce hydrogen would be hydrogen is still left. There's one gas, only one gas has been released here. It's not going to be hydrogen here, but it's going to be water. Write water there. Liquid water. Now, we need to balance the equation. In balancing this equation, what we need to do here is, in balancing this equation, we have oxygen here. There are two oxygen atoms that are here. Now, oxygen here is only one. So, there are two hydrogens here. If we put two here, it's not going to balance the oxygen. So, in order to balance the oxygen here, let's put a 2 here. If we put a 2 here, there is 2 oxygen here and other 2 here, therefore making a total of 4 oxygen. So we will balance here, we put a 4 here. We put a 4 there. We have 4 oxygen here on the left, and on the right we have 2 and plus 2. Oxygen is balanced. For hydrogen, we have 2 times 2, we have 4 hydrogen on the right. On the left, we have 4 hydrogen. So the equation here is also balanced. On the ions, there are 4 minuses here. 4 minus here, 4 times this minus is 4. Here we have 4. So our equation is complete. Now, explain how the ionic half equation shows the hydroxide ion are being oxidized. How do you know that the hydroxide ion are being oxidized? Now, we can do it by using here the hydroxide ions. Oxidation is what? Oxidation is loss of electron. Oxidation is loss of electron. We can now say that the OH ion lose electrons. One reason the OH ion will lose electrons. 2, we can say oxygen, there is an increase in oxidation state from -2 to 0. Because if we calculate the oxidation state of oxygen here, oxygen, there is an increase here from -2 to what? To 0 here, because oxygen is free state here is 0. So there are 2 reasons we can give, explain how ionic equations show that hydroxide ions are being oxidized. The first thing is we can say the first reason we can give here is that the OH ion loses electron. The OH ion loses electrons. Another reason that is one. The second reason is you can say oxidation state of oxygen increase. For oxygen, increase in oxidation number. In oxidation number, oxygen increase in oxidation number from -2 to 0. oxygen increase in oxidation number from -2 to 0. Then another reason is the OH ion lose electrons, since oxidation is loss of electron. Then it takes us to the C part of this. The C part of this. Describe what the student observed at the cathode. At the cathode, something is going to happen at the cathode. Something is going to happen at the cathode. At the cathode, since at the cathode, this is electrolysis of sodium chloride, aqueous sodium chloride. Remember that for the electrolysis of aqueous sodium chloride, see what happens. Aqueous sodium chloride. There is sodium chloride. This is sodium chloride, aqueous. Since it is aqueous, it means water is involved. There is the anode. There is a cathode. The anode is positive. Now, water is being involved. In that case, there is water too. Since it is aqueous sodium chloride, there is sodium chloride and there is also water involved. Water will produce two ions. And which are the ions? The ion that water will produce will be the ion that water will produce will be the hydrogen ion and the OH ion. Sodium chloride will produce sodium ion and the chloride ion. So now, at the anode is the positive electrode. So the chloride ion will be here, will come here. The chloride ion will come here, and the OH ion will also come here. Now at the cathode, the sodium ion will come there, and the hydrogen ion will come there. Checking at our electrochemical series or our reactivity series, you will see that the one below at the electrochemical series will be the one that will be discharged. For the anions, the one below will be the one to be discharged. So we have the chloride and the hydroxide ion. So the one that is going to be discharged here is going to be the hydroxide ion. That is the hydroxide ion that is going to be discharged at the anode. Then at the cathode, we have there are two cations, the sodium ion and the hydrogen ion. The one below in the electrochemical series will be the one that will be discharged. Look at the sodium ion is right up, and the hydrogen ion is right down. So hydrogen ion is the one that is going to be discharged in this reaction. So for that reason, the hydrogen ion is the one going to be discharged. Therefore, at the cathode, the reaction that is going to take place at the cathode will be for the hydrogen ion. And if this reaction occurs at the cathode, therefore at the cathode, what we are going to see will be at the cathode, because initially at the anode it was the OH. We are done with the OH. Now at the cathode, what is going to be discharged is the hydrogen ion. Is the hydrogen ion that will be discharged. So writing the equation at the cathode, this is what we are going to observe. The hydrogen ion in aqueous condition is going to do what? It's going to gain electrons. It's going to gain electrons to form what? A hydrogen gas will be produced. In balancing this, we will have 2 here. And in order to balance it, there will be 2 electrons that will be gained. So now, in this case, What is happening here will be there is a reduction. Reduction is taking place here. We call it reduction. Why we say it is reduction? Because there is gain of electron. Why we say there's a reduction is there is gain of electron, or there is reduction in the oxidation number. Hydrogen ion is from +1 to 0. From +1 to 0. Either you say it is oxidation, there is reduction taking place here because there is a reduction in the oxidation number from +1 to 0, or is because hydrogen ion gains electron, there is gain of electron. So hydrogen is released. Hydrogen is released at the cathode, and what is observed there will be either effervescence, or you can say there is fizzing. Effervescence is observed, fizzing is observed, indicating the release of a gas. So let's go back to our question and present our answer the way we have discussed. Here, the C part will describe what the student observed at the cathode. At the cathode, there is effervescence. There is effervescence. Effervescent. Or what we can say, fizzing. Fizzing. Or you can also say, bubbles of gas are observed, because you will see bubbles of gas indicating the release of a gas. Effervescent or fizzing indicating the release of a gas. Indicating the release of hydrogen gas. So now write the equation, write the ionic half equation for the reaction at the cathode. The ionic half equation is simple, just as what I have just described there. We have hydrogen. There's hydrogen in aqueous. There is gain of electron. A hydrogen gas is being produced. We need to balance our equation. We have a 2 here to balance the hydrogen. Then the 2 ions, there are 2 ions here, so there will be a 2 here, here. And that is how you can, that is the equation. And that is how you get it. The E part of it, we will have the student repeats the experiment using concentrated. The student repeats the experiment using concentrated aqueous sodium chloride. Concentrated aqueous sodium chloride. This is the E part of it. Concentrated aqueous sodium chloride. Describe what the student observed at the cathode. Again. Okay. It is concentrated. Let's go back again. Concentrated aqueous sodium chloride. Now it is concentrated. Now it is concentrated. As it is concentrated, we are going to deal only with the hydrogen ion, and the chloride. So now, at the cathode, what will be observed will be there will still be fizzing or bubbles of gas. So now, because it is concentrated, what is going to be released at the anode? Let's go back to the explanation. Because it is concentrated, what is going to be released? There are two ions here. What is going to be released here? There will be no OH again. Instead of the OH, what is going to be released will be the chloride ion, because the OH was coming as a result of the water. So there will be it will be chloride that will be deposited at the anode. Chloride will be deposited at the anode. Chloride will be deposited at the anode. So now let's go back. Now, describe what the student observed at the cathode. At the cathode, there will be the hydrogen gas will be still produced. At the cathode, describe what the student observed at the cathode. There is fizzing and bubbles of colorless gas. There is fizzing, you will observe fizzing. I said it's still a gas that is being produced. Fizzing. You can say fizzing. You can say bubbles of colorless gas. Bubbles of colorless gas. Now, at the cathode, what do you think is still going to be? Is still a gas that will produce there. Now, at the anode, is still a gas that is going to be produced there. I said that instead of the OH being deposited at the anode, as I told you, what will be deposited instead of the OH being deposited at the anode, because there are two anions, the chloride and the OH. But this time as also it is concentrated aqueous sodium hydroxide. Because it is concentrated, OH is no longer there. So it is only the chloride ion that is going to be deposited. And it's the chloride ion that is going to undergo a reaction at the anode. Is going to undergo a reaction at the anode. It's going to undergo a reaction at the anode to do what? And a gas will be produced. Chlorine gas will be released. So now, let's go there. Now, at the anode, describe what the student observed at the cathode. Then at the anode, it will still be fizzing. What will be observed at the anode will be, there will be fizzing. You can say fizzing and bubbles of chlorine gas, or you can say a green gas, because you will not know whether it is green gas. Fizzing or bubbles of green gas. Bubbles of green gas are released, because this is what is going to happen there. For the purpose of revision, this is what is going to happen at the cathode. Let me just put it there. This is what is going to happen there. It will be two aqueous lost electrons, chlorine gas plus 2 electrons. That is what is going to happen there. So what is observed will be fizzing or bubbles of green gas. That is the chlorine gas that is going to happen at the anode. Then, then the second part of it, the student added litmus to the solution after electrolysis of concentrated aqueous sodium chloride. The student added what? The student added litmus to it. State the colors seen in the solution. Give reason for your answer. Now, the litmus here, the litmus paper here, since it is sodium chloride, it is sodium chloride. Now, a sodium chloride is dissolved in water. The sodium chloride is dissolved in water. We will have sodium hydroxide and hydrogen chloride. So sodium hydroxide will give us an alkali solution. It will give us an alkali solution. So therefore, if we now put a litmus paper there, an alkali solution, indicating that that is an alkali solution. It is alkali, and if it is alkali, the litmus paper will not turn blue, it will not turn red, but it will turn blue because the solution is alkali. So the color of this, it says state the color seen in solution. Give the reason. Okay, the color will be litmus turns blue. Litmus turns blue because it is an alkali solution. Our reason, as I've just explained, is because the solution is alkali. The solution is alkali because the solution is alkali. That is sodium hydroxide, sodium hydroxide. The solution is alkali. Formed. The solution is alkali formed from uh, from sodium chloride and water. And this is how you can see how the whole thing is formed. We have sodium chloride plus water. It will give us so litmus turns blue. The solution is alkali, formed from sodium chloride and water. That is it. Okay, let's go to F. Let's go to F. Let's go to F. Carbon electrodes are used because they are inert. State another element that can be used instead of carbon. Fellow learners, it should be noted that carbon is always used because carbon electrodes or graphite electrodes are always used because they are inert, they are inactive. And there is always another one element that is always used. If you can't find the graphite or what we call the carbon electrodes, the next element you can use is a platinum. So our answer here is platinum. Okay, it takes us to the question number 3. Question number 3. On question number 3, we have to do with chemical energetics, or what we call the enthalpy changes, energy changes, enthalpy changes, that are under chemical energetics. Nitrogen reacts with fluorine to form nitrogen trifluoride. The chemical equation can be represented as shown. We have nitrogen triple bond, 3 molecules of the fluorine to give nitrogen 2 moles of nitrogen trifluoride. Some bond energies are shown in the table below. We have the bond energy in kilojoule per mole. Calculate, the question now says, calculate the energy change for the reaction between nitrogen and fluorine using the following steps. Okay, using the following steps. Remember, bond breaking, bond formation, bond making, or bond breaking. In bond breaking, energy is absorbed. In bond breaking, energy is absorbed, and it is always endothermic, and it has a positive value. In bond making or bond formation, energy is released. It has a negative value, and it has a negative value, and the value is and it is exothermic. Let's get started with this. Energy taken in to break bonds, and bond breaking takes place, but in bond breaking takes place in what? In reactants. Energy is absorbed to break bonds in the reactants. Energy is released when products are formed. So we are now going to concentrate only with the reactant now. Energy taken in to break bonds. Only reactants are involved. So we now go into reactants. So reactants here we have bond breaking. We will have nitrogen, 3 bonds, plus 3 fluorine, 3 F. So in this case, nitrogen bond energy for the nitrogen molecule, three bonds, we have 945 kilojoule per mole. So here is 945 plus fluorine is 160 times 3. There are 3 moles of fluorine molecule. We have 3 into 160. The total here, summation of all this will be, since I said energy is absorbed in bond making, in bond breaking, the value is supposed to be what? Endothermic, and that is a positive value. We will have a plus 1425 kilojoule. Will be kilojoule. Will be kilojoule. Now, okay, our value here is plus 1425 plus 1425 kilojoule. Energy released when bonds are formed. Remember, I said, energy released when bonds are formed. So now, when bonds are being formed, Energy is when bonds are being formed, we are doing what? It involves the products. It involves but the products. Energy is being released to the surrounding. It is exothermic, and the value is what? Negative. Let's get there. So looking at the products there, we will have looking at the product there, we will have um, 2 into F, nitrogen, F, nitrogen, F. How many nitrogen fluorine bonds are here? 1, 2, 3. And the nitrogen fluorine bond is 300. It is 300. Is 300. So 1, 2, 3, that is 3. That is 3 times 300. 3 times 300. Now, there are 2 moles there, times 2. And that will give us what? It will give us a total of 1,800 kilojoule. 1,800 kilojoule. But remember, 1,800 kilojoule. But remember that energy released when bonds are formed. Energy released when bonds are formed. Our answer will be what? Our answer will be it will not be when bonds are formed. That is exothermic minus 1800. Now, energy change during the reaction. The energy change during the reaction, there are 2 ways. Energy change, you can add these figures and you have the energy change during the reaction. So the energy change during the reaction, you can either say it is 1,800. Energy change during the reaction will be what? It will be energy change during the reaction. Energy change will be energy in bond breaking minus energy in bond formation. Energy, that is bond breaking energy in breaking bonds minus energy in bond formation minus energy in breaking bond minus energy in bond formation. So in that case, in breaking bonds, we have 1,014 25 1425 minus 1425 minus 1,800 minus 1,800. So what will be our value? Our answer here will be what? Minus 375. That will be equals to minus 375. So the value here, as I earlier said, will be you can do this here. That is 18 kilojoule. So it's 1,800 kilojoule. Now that it is 1,800 kilojoule. So energy change during the reaction. Energy change during the reaction. Energy in breaking bonds minus energy in bond formation will be 1425 minus 1,800. The difference will be minus 375 kilojoule. Method number 2 that you can use in solving this problem. Now, method 2. Method 2. Here we said energy is taken in to break bonds, and breaking bonds is an exothermic, and the value is positive. This is plus 14 this is plus 1425. This energy is energy, that is kilojoule, energy taken in to break bonds. That is energy for breaking bonds, bond breaking. Then, energy released when bonds are being formed. As I earlier told you, when energy is released to the environment, it is exothermic and it has a negative value. So, for bond formation, we will have, instead of 1,800, we will have negative 1,800 kilojoule. That is bond formation. That is method number 2. Now, the enthalpy change or the energy change will be what? Energy change. The energy change will be the endothermic reaction, which is bond breaking, plus the exothermic, which is bond formation. That is bond breaking, plus bond formation. And the formula and the answer will be what? Plus 1425 minus, we are just adding it, plus, that is negative 1,800. It will be the same thing as, it will still be negative 375 kilojoule. So, if you want to use the formula for energy in, so the tip for a tip for the learners, if you want to use the formula energy in breaking bonds minus energy in bond formation, do not put a negative sign here, please. Do not put a negative sign for the exothermic reaction. But if you don't want to use the formula for energy in breaking bonds minus energy in bond formation, you just want to add everything. Make sure that for bond breaking it is positive, and for bond formation it is negative. Then add everything, you will still have the same answer. So this is method 2 and this is method 1. So by using this, you will have the same answer. So now, our question now is 2. Use your answer to 1 to deduce whether the reaction is endothermic or exothermic. You have observed it. It is clear that because the value is negative, it is an exothermic reaction because there is formation of nitrogen trifluoride. It ends in the formation of a product. So the reaction is exothermic. So there is bond formation. It is exothermic. It is exothermic. Now, reasons. There are reasons you can give. The reasons I can give here is this. Energy release in bond formation is more energy release in bond formation is more than energy absorbed in bond breaking. I said energy release in bond formation is more than energy absorbed in bond breaking, or the enthalpy change has a negative value. The reason here for the purpose of revision, reason for this answer. For the purpose of revision, the reason is that energy released in bond formation, energy released in bond formation is more than energy absorbed. More than energy absorbed in bond breaking. Another reason is that that is reason number 1. I can still say the enthalpy change has a negative value. That is why it is positive like that, a negative like that. The enthalpy change or the energy change, the enthalpy or energy change has a negative value. That's okay. So let's go to the other section of the question. Question number 4. Question number 4 has to do with some ions. Question number 4. Look at the table shows the masses of some of the ions in the 1000 cm cube of fruit juice. The name of the ions are there. The formula of ions are there. The mass of the ion in 1000 cm cube of fruit juice is there. And in milligram. Okay, we have it from 1571 and right to 85. A. Answer this question using only the information in the table. 1. State which positive ion has the lowest mass in 1000 cm cube of fruit juice. The lowest mass here is 2, but that is not a positive ion. The positive ions are this 15, no. Your sodium ion has the lowest, that's 3 milligram in 1000 cm cube. So our answer here would be, um, our answer will be, for 1 will be sodium ion. Sodium ion for 1. Sodium ion. A1 is sodium ion. Give the formula of the ion in calcium sulfate. Calcium sulfate is made up of calcium and calcium ion and sulfate ion. So we will have calcium ion here. Give the formula of that. That is calcium 2 plus and sulfate 2 minus. That will be it. Now, calculate the mass of magnesium ion in 250 cm cube of fruit juice. Okay. Okay. We can now say in 250 cm cube, the mass, magnesium. What is the mass? Magnesium has 160 mg. Okay. Let's see if we want to do this. We can say if simple proportion is very simple. If 1000 cm cube contains 160, 1000 cm cube contain okay. If 1000 cm cube contain 160 milligram of magnesium ion. Therefore, 250 will contain X, and our value of X will be 250 times 160 all over 1000, and that will give us 40 mg of magnesium ion. Mg of magnesium ion. So it will be 40 mg, 40 mg. We'll have 40. Excuse me. Describe a test for calcium ions. A test for calcium ion, referring to our test for cations. A simple test for calcium ion will be on adding aqueous sodium hydroxide to a solution containing calcium ion, white precipitate are formed and do not dissolve in excess. That is just all. That is just all. Or adding aqueous ammonia to a solution containing calcium ion, no precipitate are formed. It's simple. Okay. Let me say the simple test is adding aqueous ammonium to calcium ion. Adding aqueous ammonium or aqueous sodium hydroxide. Aqueous sodium hydroxide, the test, adding aqueous sodium hydroxide to a solution containing a solution of calcium ion. The observation, adding aqueous sodium hydroxide to a solution containing calcium ion, the observation will be that white precipitate are formed and do not dissolve in excess. Observation, white precipitate formed. White precipitate formed do not precipitate formed do not dissolve in excess. So on adding aqueous sodium hydroxide to a solution containing a solution of calcium hydroxide ion, what you will observe will be white precipitate formed that do not dissolve in excess. Alternatively, you can say, adding aqueous ammonia to a solution containing this adding aqueous ammonia to a solution containing calcium ion what you will observe is that no precipitate are formed. No precipitate are formed. So the test is on adding aqueous ammonia to a solution containing calcium ion, our observation will be no precipitate are formed. But if you are using but sodium hydroxide, addition of aqueous sodium hydroxide to a solution containing calcium ion, white precipitate are formed that do not dissolve in excess. That is a simple test. Then ammonium ion, 4C. Ammonium ion are present in most fertilizer. Ammonium ion contain nitrogen. Name two other elements present in most fertilizers. Two other elements that are present in most fertilizers are, obviously you should know about NPK. N is nitrogen, P is phosphorus, and K is N is nitrogen, P is phosphorus, and K is potassium. So if nitrogen is already here, if nitrogen is already here, other two elements that are involved in NPK are what? One, phosphorus. Let me say phosphorus. Phosphorus P. And there is potassium. Potassium, which is K. Okay. Let's move to question number 5. Question number 5 has to do with chemical reactions. It has to do with chemical reactions. 5A. Oxygen is produced by the decomposition of hydrogen peroxide. Manganese 4 oxide is the catalyst for this reaction. What is meant by the term catalyst? What is a catalyst? A catalyst is a substance that speeds up the rate of a chemical reaction but remain unchanged at the end of the reaction. Substance that speed up the rate of a chemical reaction but remain unchanged at the end of the reaction. So let me say a catalyst is a substance that speed up the rate of a chemical reaction, that speed up the rate of a chemical reaction, but remain unchanged. Remain unchanged at the end of the reaction, or it is recovered at the end of the reaction. It is regenerated at the end of the reaction. So a catalyst is a substance that speeds up the rate of a chemical reaction but remain unchanged at the end of the reaction. Now, a student measured the volume of oxygen produced at regular time interval using the apparatus shown. Large lumps of manganese 4 oxide are used. Large lumps. That is manganese 4 oxide, aqueous hydrogen peroxide. That was used, the gas syringe that was used in collecting it. Now, a graph of the result is shown below. The volume of oxygen that was being produced was plotted against the time that was taken. What happened to the rate of this reaction as time increases? In your answer, explain why the rate changes in this way. Explain why the rate is changing in this way. From here, you can say the reaction decreases as time increases, because we can now say reaction. The reaction is decreasing. You see the curve. The curve goes up as the reaction is initially the reaction is very high. As time goes on, the reaction is decreasing, as shown on the curve. It reaches a time where the reaction is constant. That is, all the reactant has been completely used up. So in that case, we can say reaction decreases as time increases. Then we give our reason. Reaction rate reaction rate decreases. Reaction rate decreases as time increases. Increases. As time increases. Because we are not going to give a reason. Reaction rate decreases as time increases because one, hydrogen peroxide is used up, and this decreases the number of colliding particles. Our first reason is one, hydrogen peroxide is used up. Hydrogen peroxide is used up, and this decreases, and this decreases. It decreases, and this decreases the number of colliding particles. We can say the number of colliding particles, colliding particles. Another reason is that the reaction rate decreases as time increases because decrease in the frequency of collision. Because when the reacting particles, when the number of reacting particles are decreasing, there is a decreasing number of decrease in the frequency of collision. Decrease in the frequency of collision or colliding particles, because the number of colliding particles have reduced, so the frequency of the collision is going to decrease. Another reason is you can still base on this, you can see a decrease in the number of successful collision. Decrease in the number of successful collision. Once more, now, reaction rate, I said reaction rate decreases. Reaction rate decreases as time increases. Because hydrogen peroxide is used up, and this decreases the number of colliding particles. Another reason is because when there is a decrease in the number of colliding particles, there is a decrease in the frequency of collision. And when there is a decrease in the frequency of collision, there is also a decrease in the number of successful collision. So any of these reasons will give you some marks. Okay. The C part of it, it tells you the experiment is repeated using the same mass of manganese 4 oxide. Powdered manganese 4 oxide is used instead of large lumps. All other conditions stay the same. Sketch a graph on the axis in B to show how the volume of oxygen changes with time. Remember that when the same mass is being used, now this time around, instead of the lumps, large lumps, we have decreased the sizes into powder. Now it is in a powdered form. Now in the powdered form, we are now increasing the surface area of the reacting particles. Remember, the surface area has a role to play in the rate of a reaction. So by reducing it into a powdered form, will increase the surface area. And when there is an increase in the surface area, there's going to be an increase in the rate of reaction. So in this case, when there is an increase in the rate of reaction, the graph is not going to be like this, but there is the peak of the graph will show how it is. In that case, let me show how the graph is going to look like. It is something like this. Oh. Oh, I'm still trying to do it like this. Oh, don't worry, please. I'm coming back to it. Okay. That is how the curve is going to look like. The curve is going to be like that because the curve is going to be like that because the rate of reaction has increased. The rate of reaction has increased. This is how the curve is going to be like that. Here, this rate is faster than this. The rate of reaction here is faster than this one. It has a steep curve, unlike this other one. Okay, Let's proceed to the D part. The D part, the terms of particles. In terms of particles, explain what happens to the rate of this reaction when the temperature is increased. When the temperature is increased, more particles will gain kinetic energy. When temperature is increased, when the temperature is increased, what happens when temperature is increased? More particles, one, we can say one, more particles will gain kinetic energy. More particles will gain kinetic energy. More particles will gain kinetic energy. More particles acquire energy equal to or above the activation energy. More particles acquire energy will acquire energy equal to or above the activation energy. The activation energy. There are more frequent successful collision. There are more successful collision between particles. Three, we can say there are more frequent successful collision between particles. Thus increasing between particles, thus increasing the rate of a reaction between particles, thereby increasing the rate of reaction. Thus increasing the rate of reaction. So in trying to explain this, based on the curve, after changing the lumps into powder, we have increased the surface area of the reacting particles. The number of particles now have increased. There's increase in collision, resulting in an increase in the rate of reaction. But in terms of increase in temperature, we can now say when the temperature is increased, more particles will gain kinetic energy. More particles acquire energy equal to or above the activation energy. There are more frequent successful collision between particles, thus increasing the rate of reaction. It's okay. Let's go to the E part of it. The E part of it has to do with calculation again. It is written, the equation for the decomposition of hydrogen peroxide is shown. 250 cm cube of aqueous hydrogen peroxide forms 48 cm cube of oxygen at room temperature and pressure. Calculate the concentration of aqueous hydrogen peroxide at the start of the experiment using the following steps. Okay. Now, we have to calculate the number of moles of oxygen formed before getting to the concentration of hydrogen peroxide. To calculate the moles of oxygen, what do we do? Moles of oxygen. Remember that moles of oxygen, there is a formula here. Look at this triangle. Number of moles when we are dealing with a molar volume, the molar volume of a gas. When we are dealing with a molar volume, the number of moles is equal to what? Is equal to the volume in dm cube divided by the molar volume. The molar volume, which is 24 dm cube. Now, so we need to have the volume in dm cube and divide it, we'll have the number of moles. In that case, what do we do? Moles of oxygen will be what? The moles of oxygen will be moles of oxygen moles of oxygen will be what? Will be the volume in dm cube divided by molar volume. Molar volume in dm cube too. Molar volume in dm cube. And that will be equal to what? That will be the volume of oxygen was what? The volume of oxygen is of hydrogen peroxide. We have 25 cm cube of aqueous hydrogen peroxide forms 48 cm cube of oxygen. So the volume of oxygen is 48 cm cube. And in dm cube, 48 divided by 1000, we will have 0.048. It will be 0.048 dm cube. Divided by the molar volume is the molar volume of a gas. 1 mole of a gas occupies 24 dm cube. So the molar volume of a gas is 24. Is 24 dm cube. 24 dm cube. So now we will have 0.048 dm cube divided by 24 dm cube. What we'll be having will be 0.002 moles. That is 0.002 moles. That will be the number of moles of oxygen. Now, using this formula here, now again, deduce the number of moles of hydrogen peroxide that decomposed. The number of moles of hydrogen peroxide. From our equation, it should be noted that from our equation, This is our equation up here. From our equation, let me just put it here for you. Equation says it is hydrogen peroxide is 2. Hydrogen peroxide decomposes to give 2 water. Hydrogen peroxide, which is aqueous, to give water, which is plus oxygen. Now here, 2 moles of oxygen will give 1 mole of this. 2 moles of hydrogen peroxide will give 1 mole of oxygen. Then how many moles of hydrogen will be produced by this number of moles of oxygen that we have calculated? Let's get back there. From our equation that we have just said, 2 moles of this give 1 mole of oxygen here. So you can say 2 moles hydrogen peroxide gives 1 mole oxygen. Then X moles of oxygen, hydrogen peroxide, X moles will give what? X moles will give the number of moles of oxygen, which is 0.002. We will now our X will be what? Our X will be equals to what? Our X moles will be equals to what? Our X mole will be equals to 0.002 times 0.002 times what? Times 2, which will be equals to what? 0.002 times 2. We will have 0.004 moles. 0.004 moles of hydrogen peroxide. So 0.002 times 2, that will be 0.004 moles of hydrogen peroxide. Calculate the concentration of hydrogen peroxide. Concentration is what? Concentration is very simple. Our concentration here will be what? Our concentration here, will be in mole per dm cube. Our concentration will be equals to moles divided by volume in dm cube. In dm cube. But the volume of hydrogen, the volume of hydrogen peroxide was in cm cube, 25 cm cube of aqueous hydrogen peroxide. So we need to divide that volume by 1,000. So the number of moles of hydrogen peroxide are what? We have 0.004 divided by 25 all over 1,000. 1,000. When we divide this will be equals to what? 25 divided by 1,000, it will be 0.004 divided by 0.025. And when we divide this, we will have 0.16. And therefore, our answer here will be 0.16 mole per dm cube. We are mole per dm cube. So now, that will be 0.1 mole per dm cube. Oxygen F. Oxygen can be produced by the decomposition of potassium chloride 5. The only product of this decomposition are potassium chloride and oxygen. Write a chemical equation for this decomposition. Our chemical equation is very simple. We will have potassium chloride, decomposition. We will have potassium chloride and oxygen. Potassium chloride plus oxygen. Oxygen gas that is being produced. Okay, balancing the equation here, we have 2 oxygen here. Now, if I put a 2 here, let me put a 2 here. Okay. Yes. Okay. Oxygen, we have 3 times 2 is 6. 6 oxygen. 3 times 2 is 6. Oxygen here will be what? Yeah, 2. So if we put a 3 here, it balances the oxygen. Then 2 potassium and 2 chlorine, we put a 2 here. And the equation now is balanced. Now it takes us to the last, one of the last section of the paper, which is on molten on electrolysis. Molten magnesium bromide is electrolyzed. The incomplete apparatus is shown. Complete the diagram by labeling the anode and the cathode, adding the power supply and connecting the wires. Okay, these are the 2 electrodes. These 2 electrodes are, they are the 2 electrodes. How can we put them? It should be like this. Oh. Now, not to scale, not really to scale. Okay. Labeling the anode and the cathode. This is the anode. This is the cathode. The cathode is the negative electrode. That is, then the anode is the positive electrode. Leveling the solution here is Now, I can now conveniently say this is the negative electrode is what we call the cathode. The positive electrode is what we call the anode. The electrolyte, this is what we have magnesium, solution of magnesium 2 plus, and the bromide. And we call this electrolyte. This is the electrolyte. The electrolyte. Now, label the anode and the cathode. This is the anode, which is positive electrode. The cathode is the negative electrode. Adding the power supply and connecting wire. This is the power supply, and these are the connecting wires here. These are the connecting wires. Okay. Now, 2. Predict the product of this electrolysis at the positive electrode. At the positive electrode, what is going to happen here? At the positive electrode, what we are going to have will be this molten magnesium bromide. Okay, here we are going to have molten magnesium bromide, and this is what is going to be. Remember, we will have this magnesium bromide is going to give us in solution magnesium bromide. When it breaks in solution, in aqueous solution, is going to give us the magnesium ion, and it is also going to give us the bromide ion, that is aqueous. So when it breaks down, this will go to the cathode and this will go to the anode. So this will go to the cathode, goes to the cathode. This will be the cathode. The cathode is the negative, and this will be the cation will go to the cathode. This will go to the cathode. And this will go to the anode. So what happens here is predict the product of this electrolysis at the positive electrode. The positive electrode is the anode. So at the anode, this will be the reaction. The product of the electrolysis at the product of electrolysis here will be what? Bubbles of brown gas will be produced. So here, for the purpose of revision, at the anode, this is what happened. Anode, what happened will be, it is 2 bromide. The 2 bromide ion will do what? At the anode, the 2 bromide ion will give back the electrons, the lost electrons, to have bromine, the bromide gas that is being produced, plus 2 electrons. That is what the bromine gas is going to be produced. Then at the cathode, what is going to happen at the cathode will be, there is reduction, there will be M2 plus, there is gain of electrons. To do what? And magnesium is deposited. Magnesium solid is being deposited. So now, predict the products of these electrolysis at the positive electrode. Just give exactly what is being done there. So the equations were to guide you on how you can get your answer on what will be produced at the cathode and at the anode. So now, what will be produced at the positive electrode? The positive electrode is the cathode will be bubbles of brown bromine gas. Bubbles of brown bubbles of brown bromine bromine gas based on our equation. Bubbles of brown bromine gas are produced. Then at the cathode is the negative electrode. At the cathode, we will have magnesium solid is deposited. Magnesium solid is deposited. Magnesium solid is deposited. Now, B part of it, the electrode must be able to conduct electricity. One, give one other property that the electrode must have. The only property, one other property that the electrode must have is that for them to conduct electricity, they must be inert or inactive. Give one other property that the electrode must have, must be inactive or inert. Must be, excuse me, must be inert or inactive. Name a suitable element that can be used as an electrode. Another element that can be used as an electrode, a suitable element, is, I said, we can say carbon or graphite electrode. So the suitable element is carbon or graphite. Carbon, or what we can say graphite, or platinum. That is a suitable element that can be used. Carbon, that is graphite, or platinum. At the C part of it, aluminum, excuse me, aluminum oxide is a compound present in aluminum ore. Name an ore which contains aluminum oxide. It should be recalled that aluminum oxide, the ore that contains aluminum oxide is a bauxite. That is a bauxite. So it is bauxite. 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 That is what we call aluminum to oxide. That is bauxite. To predict the product of electrolysis of molten aluminum oxide at the positive electrode and the negative electrode. It should be remembered at the electrode, at the electrode, it should be remembered that remember that aluminum, as I told you, I said aluminum in the extraction of aluminum for the purpose of revision. Aluminum is extracted from bauxite ore. Aluminum oxide is not reduced by carbon monoxide or any other reducing agent. For this reason, it can only be extracted by electrolysis. It should also be noted that this will require a lot of electrical energy, making it expensive. So, aluminum will first be dissolved in a molten cryolite so as to improve the conductivity of the electrolyte. And this will decrease the temperature of the electrolyte and greatly reduce the total energy that is required. So when for this electrolysis to occur, what will happen is this. For the purpose of revision, what is going to happen is that this is aluminum oxide. Let's say this is O3. In the aqueous solution, this is how it will break down to what we call aluminum plus the oxygen, the oxide. These are the ions, and if we were to balance it, we will have a 2 here, we will have a 4 here, we will have a 2 here, so this will be there will be a 4 here, there will be a 4 here, and there will be a 6 here. So in that case, at the anode, this will go to the anode. Anode is the positive electrode, and the positive electrode will receive this. This will go to, and this will go to, this will go, oxygen will go to the anode, and the aluminum ion will go to the cathode. And we'll go to the cathode. Now we have been told. Predict the product of electrolysis. Predict the product of electrolysis of molten electrolyte at the positive electrode. The products, predict the product. So the product of electrolysis here at the anode will be what? It will be oxygen. Positive electrode, that is I said at the anode, oxygen will be produced. So now, what will be produced at the anode will be oxygen. Predict the product, oxygen. Oxygen, well, that is O2. Now, at the negative electrode, the negative electrode is the cathode. The negative electrode is the cathode, and what will be deposited at the cathode is a molten aluminum, which is solid. The molten aluminum, which is solid. It is molten aluminum, which is solid. Aluminum. Aluminum. Now, it is possible at the cathode we can have this equation. That is why I say at the cathode The equation at the cathode will be aluminum 3 plus 3 electrons to give the aluminum solid. At the anode, what you will have at the anode will be, it is 2 oxygen, 2 minus, which is the gas, plus, no, yeah, it has to give the electron, not, yeah. Yes, we'll have, for the purpose of revision, will be oxygen plus 4 electrons. Plus 4 electrons. So that is this is aqueous, sorry. Okay, that is what will be observed at the anode. That's why I say at the anode, oxygen will be produced, and at the cathode, aluminum will be produced. So now, at the cathode, aluminum will be produced. That is the negative electrode. So now, question number 3. Suggest why aluminum is extracted by electrolysis and not by reduction with carbon. I earlier explained that aluminum is not reduced by carbon monoxide or by carbon or any other reducing agent because it is too expensive. It is too expensive because it will require a high amount of electrical energy. And for that purpose, they will only have to undergo but electrolysis because with electrolysis, it is cheaper. So our reason here is because aluminum is highly reactive. The first reason is aluminum is highly reactive. And the second reason is that because it is less expensive. So we can say the first reason is because it is less expensive. Because aluminum is highly reactive. Aluminum is highly reactive. Aluminum is highly reactive. Secondly, also because it is highly reactive. Secondly, because it is less expensive. It is less expensive. It is less expensive compared to reduction that requires more heat energy. It is less expensive compared to reduction that requires more heat energy. So suggest why aluminum is extracted by electrolysis. Aluminum is highly reactive. Also because it is less expensive. I can say, yeah, let me put it, okay. There are 2 reasons. Let me use this. I said the first reason is that aluminum is highly reactive. The second reason is that it is less expensive compared to reduction that requires more heat energy. Okay. Let's go to the D part of it. Bromine reacts with hydrogen sulfide. Complete the chemical equation for this reaction. Hydrogen sulfide, we will have to say bromine. That is Br2. Bromine plus hydrogen sulfide will have 2. Bromine plus hydrogen sulfide will have 2 HBr plus sulfur. Finish. The last section, the energy level diagram for this reaction is shown. We have the reactant, we have the product. Of course, this is an exothermic reaction. Explain how this diagram shows that the reaction is exothermic. Very simple. The energy release in forming product is less than the energy of the reactant. That is simple. So we can say energy release the energy released in forming product the energy released in forming product is less than the energy of the reactant, is less than the energy is less than the energy of the reactant, and this energy has a negative value. So explain how this reaction, how this diagram shows that the reaction is exothermic. We can say that the energy release, this is the energy release here. If you look at it here, the corresponding line here. So the energy release in forming product is less than, this is less here compared to the one here. It is less than the energy of the reactants. Then again, and this energy has a negative value. It is negative. So that is a simple thing there. So that is the reaction I've just mentioned. Okay. Describe the test for bromide ion. There is a simple test for bromide ion, and for halide, the chloride, the bromide, and the iodide. There's a simple test when it has to do with silver nitrate. With chloride, it will form a white precipitate. With bromide, it's a cream precipitate. With iodide, it is a yellow precipitate. So in this case, the test for bromide will be what? Adding, we can say, adding dilute nitric acid followed by aqueous silver nitrate to solution containing bromide ion. Okay, I can say adding add add dilute nitric acid, followed by aqueous silver nitrate. A silver nitrate to a solution. Add dilute nitric acid, followed by aqueous silver nitrate to solution. To solution containing bromide ion. What will be the observation? Our observation, when we add dilute nitric acid followed by aqueous silver nitrate to solution containing bromide ions, our observation will be a cream precipitate form. A cream precipitate. Cream precipitate is formed. Cream precipitate is formed. Cream precipitate is formed if bromide ions are present. So that is just all. Add dilute nitric acid followed by aqueous silver nitrate to a solution containing bromide ions. Observation: cream precipitate is formed if bromide ions are present. So that is it for the day. Once more, if you haven't subscribed to our channel, please subscribe to this channel. Also like our videos and share to other learners. Thank you for having you today. Thank you for having you today.